Let me tell you 4 small stories, and by the end, each one will have a name. Story 1. You flip a single coin once, heads or tails. Just 2 outcomes. Story 2. You flip that same coin 10 times and count how many heads come up. Story 3. You keep flipping and wait. How many flips until the very first head? And story 4. A quiet helpline rings now and then. Rare, scattered events. How many calls arrive in a single hour? 4 stories, 4 of the most useful discrete distributions: Bernoulli, binomial, geometric, and Poisson. Spot the story, and the formula follows. First, the language they all share. A random variable pins a number onto each outcome. Roll a die, and X is the top face. Flip a coin, and Y is 1 for heads, 0 for tails. It's discrete when it takes separate, countable values: 0, 1, 2. Never a smooth continuum. Its probability mass function, the PMF, simply lists the chance of each value. 2 summaries follow from any PMF. The mean, or expectation, is the long-run average, each value weighted by its probability. The variance measures spread. For every distribution, we'll write these 3 down. Start with the simplest story, a single trial with 2 outcomes. Call one success, label it 1. The other failure, label it 0. Let P be the probability of success. That is the Bernoulli distribution, the single building block everything else is made from. Its mean falls straight out. 1 times P plus 0 times 1 minus P, which is just P. On average, a Bernoulli trial scores P. For the variance, note x squared equals x here. 0 and 1 are unchanged by squaring. So E of x squared is also P, and the variance is P minus P squared, which factors into P times 1 minus P. One lovely detail. That spread is largest at P equals a half. A fair coin is the most unpredictable trial, and it vanishes to 0 when P is 0 or 1, where the outcome is certain. Now repeat that Bernoulli trial n times. Same probability P each go. And this matters. The trials are independent. Let X count the successes for exactly K successes. Think in 2 parts. First, which K of the n trials succeeded? N choose K arrangements. Second, each pattern has probability P to the K times 1 minus P to the n minus K. Multiply those together, and you get the binomial PMF, the workhorse of the whole subject. Mean and variance need no algebra. Write X as a sum of n Bernoulli trials. Expectation adds, so the mean is NP. And for independent pieces, the variances add to NP times 1 minus P. Let's see the shape. Here is binomial with n equal to 10 and P equal to 0.3. Each bar the probability of that many successes. Look where it piles up. The tallest bar sits at 3, exactly n times P, the mean. Chances rise to that peak, then tail away. That mound around the average is the binomial signature. So what does P do to that shape? Hold n at 10 and slide P. With P small bc 0.2, successes are scarce, so the mound crowds to the left, peaking near 2. Push P to 1/2, and it turns perfectly symmetric, centered on 5. A fair coin spreads its heads evenly around the middle, and with P large, 0.8, successes are common, so the mound mirrors to the right, peaking near 8. The mean NP always tracks the peak. Let's put it to work. A machine turns out items, each defective independently with probability 0.3. You inspect 5. What's the chance exactly to our defective? Straight from the PMFP of x equals 2 is 5 choose 2 times 0.3 squared times 0.7 cubed. Work the pieces. 5 choose 2 is 10. 0.3 squared is 0.09 and 0.7 cubed is 0.343. Multiply the 3 10 times 0.09 times 0.343 and you land on 0.3087, a little over 30%, and the summaries drop out. The mean is NP, 5 times 0.3, 1.5 expected defectives. The variance is NP times 1 minus P, 1.05. Now flip the question. Instead of a fixed number of trials, you keep going until the first success and ask how many trials that takes. That count is the geometric distribution. For x to equal k, the first k minus 1 trials all fail, then the kth succeeds. Multiply those, and there is the PMF. The intuition is clean. On average, you wait 1 over p trials. Rarer successes mean longer waits, and the variance is 1 minus p over p squared. Its shape is unmistakable, a staircase that only ever falls. With p at 0.2, the most likely outcome is always the very first trial, and each later value is less likely than the one before. Quick example, p at 0.2. X equals 3 means 2 failures, then a success, 0.8 squared times 0.2, which is 0.128. And on average, you'd wait 5 trials. The last story counts rare, scattered events over a fixed window, calls to a helpline in an hour, typos on a page. One parameter runs it, lambda, the average events per window. The chance of seeing exactly k events is e to the minus lambda times lambda to the k over k factorial. This is the Poisson distribution. And here's the fact worth memorizing. For a Poisson variable, the mean and the variance are the same number, both equal lambda, with lambda equal to 2. The shape looks like this: a lopsided mound near the small counts, with a long thin tail to the right for the rare busy windows. Where does that formula come from? Take a binomial with a huge number of trials n, but a tiny probability p, so tiny that the mean np stays fixed at some lambda. Rare events, enormous opportunity. Watch it converge. The pale gray bars are the true Poisson with lambda equal to 2. Now watch a binomial. Its mean pinned at 2. As I crank n upward, with only 5 trials and p at 0.4, it's a rough, blocky match. 20 trials, p at 0.1, closer already. 100 trials, p just 0.02. And now the bars are hugging the Poisson. That's the whole idea. Poisson is what the binomial becomes for very rare events over very many chances, which is exactly why it counts them so well. Let's compute one. A shop averages 3 customers every 10 minutes, so lambda is 3. What's the probability that exactly to arrive in the next 10 minutes? Drop into the Poisson formula. E to the minus 3 times 3 squared over to factorial. 3 squared is 9, 2 factorial is 2. So this is 4.5 times e to the minus 3. Now e to the minus 3 is about 0.0498. Times 4.5 gives roughly 0.224, about a 22% chance. Your turn. A player sinks each free throw independently with probability 0.6 and takes 4 shots. Find the chance she makes exactly 3. Pause and work it out. Here's the walkthrough. P of x equals 3 is 4 choose 3 times 0.6 cubed times 0.4 to the first. 4 choose 3 is 4. By 0.6 cubed is 0.216 and a single factor of 0.4 for the shot she missed. 4 times 0.216 times 0.4 gives 0.3456, about 35%. If you got that, you've got the binomial cold. Trap 1. Dropping the n. Bernoulli variance is p times 1 minus p, but binomial variance is n times p times 1 minus p. Forget the n, and every spread comes out too small. Trap 2. Forcing the binomial where it doesn't belong. It demands a fixed n, independent trials, and a constant p. If trials lean on each other or p drifts, it doesn't apply. Trap 3. An impossible k. For a binomial, K must be a whole number between 0 and n, a fraction or more successes than trials, and the probability is flatly 0. And trap 4, a poison favorite. Its mean and variance are the same number, lambda. See them treated as two different things, and something has gone wrong. Let's lock all four in. Bernoulli, 1 trial, mean p, variance p times 1 minus p, binomial, n independent trials, counting successes, mean np, variance, np times 1 minus p, geometric, the weight for the first success, mean 1 over p, variance 1 minus p over p squared, and Poisson, rare events in a window run by lambda alone, mean and variance both lambda. Every discrete problem comes down to one move. Recognize which of these four stories you're in. Name the parameters, reach for the formula, and the rest is careful arithmetic.